Here's an example of deciphering complex reaction conditions that's tied into the mechanisms PowerPoint that I've already provided. And so I'm really doing this as a way of bringing together several different ideas. One of which is that kinetics versus thermodynamics is relatively challenging to try to figure out, and that some of the signals are buried in these conditions, and so you should be paying attention to them. Although they're not necessarily as intuitive as you'd like. It's a way of tying together some acid-base concepts that you've already worked with, and it's a way of bringing together sort of the complex structures of that mechanism PowerPoint and get you to realize that there are many things that were building up over time. And so now, if you were to go back and look at that PowerPoint again, you would find that a lot of this would make a lot more sense than it did originally. So back when I was working for the drug company, I decided to take this material and go ahead and make something. And it turned out that a little bit later on, I had my intern make what I thought was going to be the same stuff, and it turned out not to be. What I did originally was I took this material and I was trying to make this stuff right here, but it, required me adding in a bit of a mild acid, which I did, and then some reagent, which is not super important, and it makes this, which again, not super important, so I'm not going to tell you what those are. But I threw in dichloromethane, and I would hope that you would recognize from the lab that dichloromethane has this structure, and I let the reaction run for, say, 3 hours or so at room temperature, and that's mostly because I set it up in the morning, and then I went to lunch, and then I came back and took a TLC plate. TLC plate looked great, so the reaction was done, and I isolated some material, and I took an NMR of it, and I thought it was actually this stuff, because that's what I was trying to make, and all of the pieces were there, it looked great, and I was done. So awesome. Okay, a little bit later I decided, hey, I need to make a lot more of this stuff, and so I told my intern Ross to go ahead and make some. But for him, what I did was I said, well, there's no reason why it needs to go as slowly as I did. Why don't you just throw in some stronger acid and heat the crap out of it, which is what this delta means, so boil it instead, and it should be done a lot faster, and you don't need to wait around all afternoon in order to get this to go. You can just set this up, and in an hour you can work it up and see what you have. So he did that, and he went and isolated some material, and he pretty proudly brings me his NMR, and I look at it and says, yep, looks great. And he then said something really interesting to me, and that was, I agree that my stuff is the right stuff, but I looked at your stuff, and it also looked like the right stuff. And I look at the two NMRs right next to each other, and they don't look like each other. And I thought, that's weird. So we investigated further, and what we learned was that, in fact, we had switched over from a kinetic condition to a thermodynamic condition somewhere in there along the way. And in fact, the material that he made was the thermodynamic product, and in fact, the material that I had made first was actually the kinetic product. So what all's going on here? Well, fundamentally, we used two very different acids. And so the pKa for para-toluene sulfonic acid is on the order of -8 or thereabouts. I mean, it's a strong acid, so I really had him crank up the acidity relative to mine, and he also cranked up the temperature quite a bit. In my case, this is mostly a pyridinium acid that's actually doing it, so the pKa is really about 5, and so this is 10 to the 13th difference there. It's a massive, massive difference in terms of acidity. And so even though he ran his for a shorter time than I did, he used a much stronger acid, and he heated it up, and so he was able to access the thermodynamic product. How do we know, by the way, that his was the thermodynamic product and mine was the kinetic product? Well, because after that initial reaction, I went back through and made both on purpose. And what I realized was that mine was forming first. So if I run the reaction slowly and with a mild acid and a long time, just long enough for this reaction to be done, then I could see this material convert completely. And only if we heated it up or added a stronger acid or something like that would it then convert on to the next product. And so basically what was happening is this. If you started with starting material at some spot on the TLC plate, it's relatively polar because it doesn't have this extra group on there, and then we allowed the reaction to run for a while, what I could observe is my reaction eventually going to some product, and once the starting material was gone, then I worked it up and isolated my material and I was happy. But if you let it go longer, it would then convert from that one into a slightly more polar product, which turned out to be the thermodynamic one. And so it is in fact possible to watch this form, and then given enough time, given enough energy, given enough heat, given enough acid in the system, it could eventually interconvert down into the other. So the reason why we know this is kinetic product is we could actually watch it show up first in the TLC plate, and then once we change the conditions, we could watch it disappear and form the other one. And since this is what happens when we heat on it and we use a stronger acid and so on, this ends up being the thermodynamic product. Also, if you look at the structures involved, the reason why this is a thermodynamic product is really because you can see this benzene ring here, and that's what makes this more stable, whereas up here we don't have the benzene ring, and though we have an aromatic system anyway, it's not as stable stable as this one. So this turns out to be the thermodynamic product. And again, we know it's the kinetic product because we saw it convert first into that. But also, this nitrogen is more accessible than this one. And in fact, we know, again from TLC experiments, that what happens is first you convert into this, and then it converts actually into the dye substitute material, and then the one falls off, and you're ending up here. And again, I can show that with a couple of experiments that we ran beyond this. But the core idea is simply this. If you have wildly different conditions, it is possible to access both material that can be formed more quickly and material that is going to be more stable in the end. Indicators like heat and extended time are indicators that you're headed toward a thermodynamic product, although in this case, the shorter time is a bit misleading because what matters here is the heat and the strength of the acid instead. So the harsher conditions in general will allow you to access the thermodynamic product almost always. The milder conditions are the ones that allow you to isolate whatever forms first, and that again is almost always true. What's confusing is that the time involved may not be the relevant consideration. What may be the thing that matters is how strong the acid is or how much temperature is around, how much heat you're pumping into the system.